Welcome to the content material for Class 12 of Engineering Statics. You should be watching this video before your 12th class. In this lesson, we will learn how to solve for reactions at connections to rigid bodies in both 2 and 3 dimensions. And we'll learn how to determine the reaction, which could be either forces or moments, at each rigid body connection. In our last class, we learned how to draw models of systems with rigid bodies using free body diagrams. Today, we will learn how to solve those systems. When solving systems of equilibrium for rigid bodies, we first draw the free body diagram. When we do that, we have to decide what are the x, y, and z axes. We also show all the forces and the couple moments acting on the body. And we label each force or moment and show their direction, including the reactions at the connections. Once our free body diagram is complete, we can set up equations for equilibrium and solve for the unknowns. In 2D, we normally set up the sum of forces in the x and y directions equal to 0. And we will choose a point and set the sum of the moments about that point equal to 0. So that gives us 3 possible equations to use. And we should choose the point for the moments where most forces intersect. So in this problem, we would choose the point B, which is here, because we see that at least 3 forces, the y component of F, By, and Bx, all go through the point B. And so by choosing that point, we can ignore those 3 forces when computing the moment. So let's look at some examples of how to do this in 2 dimensions. So in our first 2D example, we have a beam. And that beam has 2 connections. At point B, we have a pin, which we use a triangle as a symbol. And at point A, we have a roller, and we use a circle symbol. And this is a very typical problem in statics for a 2-dimensional equilibrium problem. You're almost always going to have a pin and a roller, and then some set of forces. So let's start drawing the external forces. We see this force, which I'll call F1, is oriented at a 45-degree angle. We have this force, which I'll call force 2. It's equal to 100 newtons. And F1 was 600. And we have a third force, which I'll call F3, with a magnitude of 200 newtons. Next, we have to determine the reactions at the 2 connections. So this is a pin, so we know we're going to have both an x and a y component. And I guess that the x will go in this direction and the y will point upwards. And finally, we have a reaction at point A, which can only point perpendicular from the surface, so it's going to point vertically only. At this point, we'll start solving using our 3 possible equations. So I'm going to use that the sum of the forces in the x direction are equal to 0, the sum of the forces in the y direction are 0, and the sum of the moments about a point. And I'm going to choose point B is equal to 0. The reason I choose point B is because there are 3 forces, Bx, By, and F3, all point through the point B, and therefore their moments will be 0. So we always want to choose the point with the most forces pointing through it so that we can eliminate as many forces as possible. So let's start with the sum of the forces in the x direction. Solving for Bx, we find Now we move on to solving in the y direction. So remember, we always want to remind ourselves which way is positive. So in the y direction, positive is up. So it means that the force A is positive, the force By is positive, and the other forces are negative. So F1 and its y component, sine of 45 degrees, minus F2 and minus F3. All of these will add up to 0 for equilibrium. When we do that, we can find that By So at this point, we can solve for By in terms of A, but we still have another unknown. So we're going to continue on to our third equation. We'll solve for the moment around the point B. And we're going to define counterclockwise as positive. So when we do that, we see that there are two positive moments about the point B. One is caused by the F1 y component, and the other one is caused by F2. So there are two positive moments from F1 and its distance away, which is 5 meters, and F2 with its perpendicular distance away, which is 2 meters. And then we want to subtract away the negative moment. So there's a negative moment caused by the A force, and there's also a small one from the X component. If we look carefully, that X component up here has a distance of 0.2 meters. And so there's a small negative moment caused by the X component of force 1. All of that's going to add up to 0. So when we put all the numbers in, we find that the only unknown is A. And so we can solve for A. And we find A is 319.5 newtons. And we can go back up to this equation to find that By is equal to 404. In our second 2D example, we have a lever, and so we'll draw that lever. And we see that there's one external force, I'll call that F, equal to 60 newtons, and there's a couple moment with a magnitude of 90 newton meters. And then we see that there's a pin at point A, which means we have both X and Y components to the reaction, and we have a smooth support at point B. What that means is that, again, the force can act only perpendicular to the surface. And we know this is 30 degrees here, which means this is 30 degrees. So if this is perpendicular, 90 minus 30 is 60 degrees. So now we see the orientation of the force B. And so we go through, again, solving our equations. Sum of the forces in X are equal to 0. To the right is positive. So we start with our positive forces. Well, we have AX pointing in the positive direction. And in the negative direction, we have the X component, so cosine of 60 degrees. So we see that AX is equal to the X component of B. We don't know what AX or B are, so we'll have to come back and use that equation later. Let's move on to Y, with positive being oriented upwards. Well, what positive forces do we have? Well, we have AY. In the negative direction, we have the Y component of B, so the sine of 60 degrees, and we have F pointing downwards. It's going to be equal to 0. So in this case, we can find that AY is equal to F, which we know, plus B sine of 60 degrees. So again, we have two unknowns we still aren't able to solve. So we'll move on to our final equation, the sum of the moments. Well, what point do we want to use? Well, the best point would be to choose point A, because two forces, AX and AY, move through that point. So in the counterclockwise direction is positive. And if we draw out, if this is the point A, we know that B is perpendicular to this distance, which is 0.75 meters. And this force F is perpendicular to the distance of 1 meter. And don't forget, we also have the couple moment, which is 90 Newton meters. So, if we talk about positive moments about the point A, there's only one, and that's the moment from B. So that force B times the distance. For negative moments, we have two. We have F, and we have the couple moment, which is 90 Newton meters. All of that adds up to 0. And so we're able to solve for B. B is equal to 200 newtons. Now we can go back to our equations and find that AX is equal to 100 newtons, and we can solve for AY, which is 233 newtons. There we go. Now, there is a trick we can use sometimes to simplify a problem. If we recognize that some members have only 2 or 3 forces applied to them, we can take a shortcut. The first we'll consider is a 2-force member. A 2-force member means that only 2 forces are applied to that member. For example, this member here has 2 forces applied to it. There's force A and force B. For this member to be in equilibrium, we would find that FA must equal FB. Therefore, we know that FA and FB have the same magnitude, and we also know that they act in line with each other. Therefore, FA and FB are equal and opposite in direction. A 3-force member has only 3 forces applied to that member. So for example, this beam has 3 forces applied to it. In a 3-force member, there are 2 possible solutions. First, all of the forces can be concurrent, meaning that they all point towards and coincide at a single point. Or, all of the forces can be parallel to each other. So, sometimes it can be helpful to recognize 2 or 3-force members in the system to help simplify the problem. And I'll show you an example of that. So in this example, I won't solve all the way to the end, but I will show you how you can use 2-force and 3-force members to simplify this problem. So if we look at this, we start with the main member, which is this lever, ABC. And if we start with that, we know that there's this external force, the force C, with a magnitude of 400 newtons, pointing horizontally to the right. And then we see that at the point B, there's a pin. And at the point A, there's also a pin. But if we look at the point B, we see that it's connected to this member, which would then turn out to be a 2-force member. So we know that on this member over here, member BD, there's some force acting on it here and here. Well, because it's a 2-force member, that force D and force B, they have to equal each other and be in line. So because the dimensions of this are 0.2 meters and 0.2 meters, we know that this angle is 45 degrees. So this allows us to simplify this problem because we know that the reaction at B is oriented at 45 degrees. And now we can even simplify it further because now we see that member ABC is a three-force member. So now we have a three-force member. If you remember, a three-force member can either have all of the forces point to a single point, or they can be parallel. Well, we see that FC is going this way, FB is at a 45-degree angle, so we know they can't be parallel. So actually, what we can do is we can say that all of the forces should point to a single point O. And we can actually find out that the force A points in this direction. So in actuality, the force B will be oriented in this direction. But we can see that this line will go to the point O. So if we know that this distance here is 0.4 meters, and this is 0.7 meters. And we can actually solve for that angle theta. And we can find that theta is equal to the inverse tangent, or 60.3 degrees. You could use this information to quickly solve this problem and simplify it. So by first recognizing that BD is a two-force member, it allows you to know the direction of the force FB. And then by recognizing that member ABC is a three-force member, it allows you to find the orientation of the force at A. And that will just help you to solve it faster. When solving systems in 3 dimensions, the procedure is the same as 2 dimensions. Again, draw the free body diagram, establish the x, y, and z axes, label the forces and the moments, and then set up your equations for equilibrium. Now, normally, you would have 6 equations. You can sum up the forces in the x, y, and z directions, and you can sum up the moments about the x, y, and z axes. And so these are the 6 scalar equations that you can use to solve for the unknowns in a 3-dimensional equilibrium problem. You can also do this using vectors. So if your problem is set up with vectors in Cartesian format, you might choose this approach. In this approach, you set up all of the forces in vector format and say that they add up to 0. And you choose a point, any point, in which you compute all of the moments about that point. And you sum up all of those moments equal to 0. So let's look at some examples of how to solve problems in 3 dimensions using both the scalar and the vector approaches. So in this problem, we have 3 dimensions. So the free body diagram is already given to us. We see that there's a ball and socket joint at the point A, and there's a smooth journal bearing at the point B. So what we're trying to find, and we want to know what is the force AX, AY, AZ, BX, BZ, and FC. These are all unknowns. So we have 6 unknowns, which means we need to use 6 different equations. Well, we can do the sum of the forces in the X, sum of the forces in the Y, sum of the forces in the Z, the sum of the moments about the x-axis, the sum of the moments about the y-axis, and the sum of the moments about the z-axis. So that gives us the 6 equations that we need to solve those 6 unknowns. So I'll do these in order of how this would be done the fastest way. But you might not be able to see that right away. So the fastest way we can do this is first by starting with the sum of the forces in the y direction. When we do that, we find that there's only one force in the y direction, which is AY. So if AY is equal to 0, Next, we can look at the sum of the moments about the y-axis. Now I like to draw a picture to remind myself, so if the y-axis is oriented this direction, this way is positive according to the right-hand rule. And so doing that, we see that there's one positive moment from FC acting at a distance of 0.6 meters away from the y-axis, and there's one negative moment from the force of 900 newtons acting at a perpendicular distance of 0.4 meters. And so we can use this to solve for FC. Next, we can use the sum of the moments about the x direction. And again, if the x is oriented this way, according to the right-hand rule, this way is positive. So we see two positive moments, BZ, at a distance of 0.8 meters. There's a positive moment from FC at a distance of 1.2 meters from the x-axis, and our 900 Newton force, all equal to 0. And we can solve for BZ. Now, we have a negative answer. What does that mean? Well, it means that the way we drew it, BZ, we drew it pointing upwards. But in fact, BZ is actually pointing down. So we guessed in the wrong direction. So based on our diagram. Now as we move forward, we want to still continue to use BZ pointing upwards in terms of our orientation when we build our problems, even though we now know that in fact BZ is pointing down. So next we can do the sum of the moments about the z-axis. So z points this way, so according to the right-hand rule, turning this way would be positive. Well, we find that there's only one possible moment, which means that Bx is equal to 0. Now we can do the sum of the forces about the x direction. And we see that Ax and Bx are the only x forces, and we already found that Bx is equal to 0, so that means that Ax is also equal to 0. Finally, we can do the sum of the forces about the z direction. So in the z direction, well, we have AZ, we have BZ, we have FC, and we have our 900 Newton force acting downwards, so that one's negative. So we can solve for AZ, again using our negative value. So AZ is equal to 900 newtons minus FC minus BZ. So we found that BZ was negative 450. So when we do that, AZ is equal to 750 newtons. So there we did it. We solved for 1, 2, 3, 4, 5, and 6 unknowns using our 6 equations. 1, 2, 3, 4, 5, and 6. So far in the examples we've looked at, we've used the scalar approach to solve for our moments, but we may sometimes want to use the vector approach. And so that's what I'll show you how to do in this problem. When we use the vector approach, we say that the sum of all force vectors is equal to 0, and the sum of all moments about some point are also equal to 0. And in this case, we'll choose the point A, but I'll show you that after we set up the free body diagram. So let's start by drawing this rod, which we see has a ball and socket joint. So I guess that the force AZ, AX, and AY will act in this direction. There's this force, which I'll call FC, of 200 newtons. And we have two cables here with tension. So the tension in cable BD and the tension in cable BE. With our X, Y, and Z axes oriented this way. So, first thing we want to do is define all of the vectors in terms of. So the first thing we want to do is define all of the forces in terms of vectors. So we have the force at the reaction A, which is negative AX, so it's pointing in the negative direction, negative AY, and and positive AZ. So we don't know those values. FC as a vector is negative 200 in the K direction, units of newtons. Then we have the tension in BE, it's just equal to its magnitude, and it's pointing in the positive X direction. And the BD cable, just its magnitude, which we don't know, pointing in the positive Y direction. So you can add up the sum of the forces. It's equal to 0. And so there's only two X components, two Y components, and two Z components. So if we look at the X components, we see that AX is equal to TBE, that AY is equal to TBD, and that AZ is equal to 200 newtons. So that comes from each of these. And now we can do some cross products for the moments. So I said before that I want to do that moment about point A. And the reason is because I have a lot of forces, AX, AY, and AZ, that all point through that point A. So we can take the cross product of any forces that would create a moment about the point A. So there's three forces. There's the force C, TBE, and TBD that create a moment. So we're going to take the cross product of those. Well, force FC is here. Here's the point A. So there's some vector we'll call RC that points to that force. And there's also some force RB that points to our two tensions here. So I won't solve all the way to the end, but I'll show you that you can use the cross products to solve for the moments. So if we know that RC crossed with FC, that's this, and these two cross products, so RB crossed with, and we can just sum them, TBE plus TBD is equal to 0. So what you do is you can set up the determinant for this, the determinant for that, and you can end up again with three equations that you can solve. And when you do that, go ahead and try it. hopefully you'll find that the magnitude of TBD is equal to 100 newtons, and the magnitude of TBE is equal to 50 newtons. So what you can see is that sometimes we might set it up using vectors, and we can even use the cross products to solve for equilibrium, rather than only the scalar versions. So that's it for today, and that's it for the first half of the course.